It's so small. How are you, everyone? It's so weird. It's so small today. They zoomed out for some reason. Are you guys okay with the screen? Is it okay, the screen? Yeah, it's so weird. For some reason, they zoomed out from the entire screen, and now it's almost like hello, the screen. You know, one funny thing, the class next door, they were surprised to see you guys here because last week we were online and they thought the class is empty. So they moved their class from that room to this room. And they're like, oh, you have a class? Like, seriously? How come there was no class last week? And they're telling me, like, when we are not here, they use our classroom as theirs because their classroom is too hot. I was telling them, well, we can move to we can shift to online, and then you can have this class. They're like, that would be great. But yeah, so next week, Monday, this week we'll have in-person classes today and Monday, Wednesday. Next week, Monday, Tuesday, no school. Do you guys know that? Monday, Tuesday, there is no school. And then Wednesday, we'll have an online class. So this week in person, next week online, only Wednesday. And then when we'll be back, we are going to have in person again. And from 18th, I think, Ramadan will start. And I have many Muslim students here. So do you guys prefer in person or online classes? Mostly online. I love online classes. But is there anybody who hates online classes? Like who prefer to be here in this hut? I don't mind being here, but like you guys, I prefer online. Anyway, we'll discuss that later when Ramadan starts. So for in Ramadan, we have to fast for the entire day from sunrise, not even sunrise, before sunrise to sunset. So it's so when it's hot, it's really hard to concentrate because we cannot drink, we cannot think about food. Like it's so bad if you're used to eat food. That's why if you want to have a comfortable place anywhere and then take this class, I don't mind being online for Ramadan. And Ramadan is 1 month. And then within the Ramadan, I think we have some break, I believe. So this week we have Thursday. There is no class on Thursday this week. Next week, there is no class on Monday, Tuesday. And then I forgot about the rest. But there are a few weeks, there are a few offs we have. And then from April 1st to April 9, there will be no class. Some type of break. Winter break or spring break? Spring break? Yeah. So, yeah. Okay, so I have graded your homework 1. And I was actually very happy. All of you did all the questions in details. And then you showed all the work. And I didn't have to give 3 to anyone. I gave all of you 10. Whoever submitted. There are 2 people who did not submit. So if you did not submit, you get 0. But if you do submit, you get at least 3 points for doing all the work. And if you do all of them correctly, and if you do them neatly, it makes me happy. Like there are a few of you who wrote everything so neatly and everything, and I loved grading their papers because when you write neatly, like it helps me to grade easily. And when you scribbles, blah, 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 it's really hard for me to grade. So how you did your homework, most of you did actually very well in your handwriting. Please do that in the exam. If I see a good exam, like it's really easy to grade it quickly. But for the scribbles one, it's really hard. Like I actually do look at every single step. And I might be a nice professor, but I'm actually a very picky grader. Okay. So when I grade, I look at every single step. If you miss any important step and suddenly get the result, you get points taken off. Okay. So be concise, show the work in details, and then don't skip any important steps. Like your homework, the last homework. Most of you did great. So do that in your next homework. Our next homework is coming up next week, Monday midnight. right? If I'm not wrong, 1.2, no, 1.2 due dates tonight. 1.3 will be next week. And then 1.4, since we have break on Monday, so I'm not sure whether we'll be able to finish 1.4 next Wednesday. If we don't, then next week, there will be no homework. It depends on what we finish, okay? If we can finish 1.4, then the homework will be next week. But if we don't finish, then it will be next week. So tonight, 1.2, next week, 1.3. And you're almost done with 1.3. So you can do your homework by next week, Monday midnight. And then 1.4 will decide, okay? So this is 1.3, where we talked about matrix addition, subtraction, multiplication, scalar multiplication. And we did few examples in our last class where we really multiplied 2 by 2, 3 by 3 matrices. And now today we're going to start with something easy. It says before I start, does anyone have any question? I forgot to ask you. Any question, comments, concern, complaint? Not yet. So this is from 1.3. In which of these pair the first matrix can be multiplied by the second matrix? If so, what's the dimension of the product matrix? So we don't have to multiply. Just tell me whether they are multiplicable or not. If they are, then what would be the dimension of the product matrix, the resulting matrix? For example, let me do one. The first one has 2 rows and 3 columns. So this is 2 by 3. This one has 3 rows and 2 columns. So this is 3 by 2. As long as the column in the left matrix and row on the right matrix are the same number, then we can multiply. And when you do, the product matrix will have the dimension of the outer layer, the outer 2 things. So yes, we can multiply, and the product matrix have a dimension 2 by 2. So you look at the inner 2 things. If they are same number, then the resulting matrix will have the outer 2 numbers as their dimension. Now volunteer for the next one, B. 3 by 2. 1 by 3.
And since 2 and 1 are not the same, we can't multiply.
Cannot. Good job. I have few more. Next volunteer.
The last one is 3 by 3.
3 by 3.
3 by
3 by 2.
3 multiplied together. 3 by
The result will be 3 by 2. Good job. Next volunteer. D. 2 by 2. 2 by 3. And then our result will be 2 by 3. Perfect. And I'll give you few of these in the exam, just to enjoy your math, enjoy your exam. You don't have to do math, just find out they're multiplicable or not, and then what's the result. Next one. Would you like to try the next one? Go ahead, try it. E. E. How many rows do you have and how many columns do you have?
2 by 3.
2 by 3, the first one, and the second one? 2 by 3. So can you multiply? Good job. The last one. Or do you have more? The last one.
3 by
3 by 1. 1 by 4. So you can multiply. The result will be 3 by 4. Isn't it amazing? Like you're multiplying a column with a row, just one column and one row, but the result will be a huge matrix. 3 rows and 4 columns. The next question is same thing. They're saying, well, this time reverse the multiplication. So whatever you have on the left matrix on the previous examples, now make it right, and the right matrix make it left. So switch the position of your two matrices and see whether you still can multiply them or not. So same examples, but this time instead of multiplying AB, you're multiplying B times A. And figuring out whether they're multiplicable or not.
2 by 3.
Other way around. How many rows you have?
And then
So they'll flip here.
right here.
Mhm.
Oh, 3 by 2.
3 by 2, 2 by 3. Yes, we can multiply, and we get 3 by 3. Perfect. Next volunteer. See, these are not hard. Go ahead.
By 3.
1 by 3,
By 3.
3 by 2.
1 by 2.
It will be 1 by 2. Perfect. Now let's see what happened before. We had the same two matrices, and then first one we could multiply, the result was 2 by 2. Here we can multiply, and the result is 3 by 3. For B, previously we could not multiply, but here we can multiply. So the same two matrices, in one position, maybe they are not multiplicable, but if you switch the position, they may be multiplicable. Now I have 4 more. Volunteer. See, these are here just for you to enjoy this class. These are baby thing I already know, but I wanted to enjoy, participate. 3 by 2, 3 by 3. Perfect. D. Two by 3, 2 by 2. See? 2 by 3, 2 by 3. We cannot, they're not same. Now the last one. 1 by 4, 3 by 1. We cannot. If you compare these with the previous result, for C, we could multiply, it was 3 by 2. For D also we could, it was 2 by 3. Here, none of them are possible. When you switch the position, we could not multiply them anymore. E, we could not multiply, but F, we could, and the result was a huge one, 3 by 4. Here, none of them are multiplicable. So let me ask you a question. If you multiply A by B, do you get the same result when you multiply B by A? So matrix multiplication is not, what's it called? Commutative. So AB is not same as BA. That's why you have to be very careful how you're multiplying. Are you multiplying A with B or B with A? The next topic is transpose of a matrix. Transpose means you are changing your columns into rows, or you are changing your rows into column. If you do that, the new matrix is called the transpose of the matrix. So in this example, we have A, row wise 1, 3, 4, 5, 7, 9. So when you transpose it, the 1, 3, 4, instead of being row, they become column 1, 3, 4. The row 5, 7, 9 becomes column 5, 7, 9. So their dimension, observe what happened to the dimension. A is what by what? 2 by 3, and transpose becomes 3 by 2. Can you multiply them? We can, because see, the inner dimension is the same. Now, who would like to be volunteer for giving me the transpose for 3 by 3 A matrix? 315, 101, 422. Perfect. That's all you have to do. Nothing hard. Now write down these properties and let me take your attendance. These are the properties of transpose. It is what, 29. I hate that. They didn't warn us before, right? So probably we don't have to go out. Usually they email us saying, oh, you're going to have a fire drill. Let's wait and see if other people can solve. It's annoying to go out and then come back. Ahmed. Christelle. Christian. Danielle. Eric. Florence. Franklin. No. Gassan. Gaffin Jalasi. Halil. Imran. Jackie. What they're saying, do you have to go out? Can you hear them? Okay. Good. Last name Tavarage. Is it Jerry? Last name Tavarage, right? Jerry. Jonathan. It's one, right? One Tavar. Julian. Karma. Where? Kate. Kathy. Main or man, right? Man. Matthew. Melissa. Muhammad. Muntaha. Omar C. Omar D. Prabodh. Rakmanjan. Rayat. Sadia Sattar. Two Sadia Sattar here. And Sadia Sheikh. Samuel. Soraya. Saima. Stephanie. Valerie. 1, 2, 3, 4, 5, 6, 7, 8. Gashan? No. Okay. So the first property says, if you take the transpose of the original transpose, then you get the original matrix back. For example, if you have 1, 2, 3, 4 row wise, and each take its transpose, it becomes 1, 2, 3, 4 column wise. Now, if you take the transpose of this 1, 2, 3, 4 column wise, it becomes 1, 2, 3, 4 row wise again. So this is A transpose, this is A transpose. What do you observe? A and A transpose is the same thing. So if you take double transpose, it becomes the original matrix. The next one says, if you multiply a matrix with a scalar and then take the transpose, this is same as you're multiplying the transpose by the scalar. So scalar multiplication doesn't affect the transpose. The next one is interesting. If you take the product, transpose of the product, it doesn't become the transpose of the product. It becomes it flips the position. So AB transpose becomes B transpose times A transpose. So the two matrices we have, they switch their position when you apply transpose to them. But in addition or subtraction, it doesn't matter. When you add two matrices or subtract two matrices and then take the transpose of the result, it's same as you're adding or subtracting the transpose of the original matrices. So this one is okay, but this one is weird. Multiplication flips the position of the matrix of the transpose. Okay, now one example. We are given A at 3 by 3 and B is 2. So this is easy, 3 by 3. What's the size of B? 3 by 1. Can we multiply them? Yep, because we have the same number. So what would be the result? 3 by 1. Who would like to multiply? Any volunteer? Multiply AB. Be brave. I will help you. So you want me to pick you? Nobody's confident enough. Let me refresh your memory. When you multiply, you take one row from the left matrix. So left matrix is A. You take one row from the left matrix and you take one column from the right matrix. So this is our right matrix B. So you take row and column, you multiply them element wise and then add them. And then if you have more matrix in your more column in your right matrix, you keep doing all those columns. Here, our matrix B doesn't have any more columns, only one column. So take one row from the left, multiply the B matrix. Then take the second row and then multiply the B matrix. Take the third row, multiply the B matrix. That's all you have to do. Ready? Confident, anyone? Okay. Matthew. Help me with the multiplication, please.
It'd be 6
6 plus
9
3 times 1 is 3. And then the last one, 25. So we did first row, first column. So you're done with the first entire column, first entire row. Then you go to the next one.
2
2, let me change this. So 1 times 2 is 2. Plus 0. 0 times 3 is 0.
5
Plus 1 times 5 is 5. Great. Then you go to the next row.
8
We have 8 because 4 times 2. 6 because 3 times 2. Plus 10 because 2 times 5. So what do you get? 25, 26, 27, 28. 28 plus 6. 34. 7. 24. So this is AB, AB. Now, if you do AB transpose, who can tell me the transpose of this or AB? 34, 7, 24. So this is 3 by 1 and it becomes 1 by 3. So if you don't understand the multiplication, it will be easier for you if you do them this way. So you take 3, 1, 5 and you take 2, 3, 5. And then the next one, 1, 0, 1, 2, 3, 5. Our second row. Then we have 4, 2, 2, and then we have 2, 3, 5. So this will be our product matrix. So if you think this will be helpful for you, you can always write them out this way and then do the multiplication. Also, you can do this way. Since if you forget like multiply which number to which number, you can write this down as column 3, 1, 5 and 2, 3, 5. If you look at this way, you can see clearly that you need to multiply 3 times 2, 1 times 3, and 5 times 5. So you get 6 plus 3 plus 25. This will be your first term, 34, which is here. You can also write this one down as column 101 and then 235 as column. So you're multiplying them element-wise. You get 2, 0, and 5. You add all of these. The result is 7. So this is the 7 we have. Similarly, the last one we have 4, 2, 2, and then 2, 3, 5. If seeing row is harder for you, you can write as a column, and then you can see clearly what you have to multiply. You get 8, 6, 10. The result is 24, and this is what we have here. So if you cannot do the multiplication mentally, you can always write down the row you take as a column and then multiply the column just to see which element you need to multiply in the end. Okay, so any questions so far? And now a logic question. If A is an M by N matrix, so we have this A is M by N. No, sorry, my bad. We have A is M by N matrix. Explain why the matrix multiplication A transpose A and A transpose are possible. So A has size M by N. If you make its transpose, what's the size for the transpose? N by M. So can you multiply A and A transpose? Why we can multiply? Because number of column and number of rows, number of column on the left is same as number of column on the right. So yes, we can multiply. And our result will be M by M, the outer number. If you look at the other way around, A transpose is N by M and A is M by N. Can you multiply A transpose and A? Why? Because we have the same number inside. So what would be the result for the A transpose A? What would be the dimension? N by N. So it doesn't matter what is your A matrix, it may have any dimension. When you flip the two rows and columns, they change. So thus we can always multiply them. Okay, now matrix to system of equations and vice versa. So we can convert any matrix into system of equations. And we also can convert any system of equations into matrix equation. So if you have three matrices written as AX equals B, then A is the coefficient matrix, B is the constant matrix. We already did that in our first chapter, first section, converting matrix to system of equations and system of equations to matrix. So here we are going from matrices to equation. Any volunteers? Like give me equations. Here it's matrix equation, but we want to see linear equations. You take these two. So you have 3, 5, and xy. What do you get from there? Plus 5y equals 6, the first element. So you take first row and your xy, you add them after multiplication, and that equals to the first element in your constant matrix. How about the second line? So you do 2, 7 column wise, xy. So you get 2x plus 7y, and that will give you equals to the second element in the constant matrix, which is 9. So you may wonder, why do we care? Well, we care because sometimes solving system equations is easier, but sometimes solving matrix equation is easier. So we have to know going from one place to another place, or from one format to another format. This is other way around. They gave you system equations. Now write down the matrix equation. So give me something that is on the left page. Volunteer? Mohammed, it looks like you want to try.
3, 4, 6, 7. 2, 4, 0, 2, please.
Good. XYZ column wise.
9, 11.
9, 11, 91. That's it. You're just rewriting all the coefficients in one matrix, all the variables in another matrix as a column matrix, equals to the right side of the equal sign as a column matrix. Now, if you try to solve it, so we have AX equals B. So in normal algebra, what we do is we divide both sides by A, and we get X equals B divided by A, right? This is in normal algebra. But this is not normal algebra, this is matrix algebra. In matrix algebra, we can add two matrices, subtract two matrices, multiply two matrices, but there's only one operation we cannot do. Which operation? Division. In matrix algebra, we can never divide one matrix by another matrix. This is impossible. That's why what we do is, instead of dividing, we use another new term or new concept. So we have AX equals B. We invite the enemy of A. So that enemy comes and fight with A, and A die. Okay? Do you know what's the enemy of A? It should be negative, but it's not negative. It has a negative, but not in the front. Inverse. So it does have a negative, but the negative is on the power. So it's not 1 over A. It's inverse of A. Inverse of A. Inverse of A is not 1 over A. Okay? The negative 1 is not 1 over A. it's one symbol. That symbol means it's inverse of A. So we invite the inverse of A and we multiply on the left side on both sides. So the inverse and A, they cancel out. And we get our XYZ equals A inverse times B. Since division is not allowed, so we use this trick. So that means we need to know how do we find the inverse. We're going to learn that later. But for now, that's why we need to convert system of equation into matrices, because finding inverse and multiplying with B, all of that, the computer will do that for us, okay? Or the calculator, they will do it for us. But in this class, you have to do it for yourself. But you need to know in order to tell the computer how to do it. So you need to know all these algorithm. That's why you're going to do all this algorithm with baby matrices, like 2 by 2 or 3 by 3. And then for the rest, you can just tell computer to do it. Okay? So let's see. Let me skip this. This was easy. Oh, we're done with 1.3. Cool. So for the homework for 1.3, which is next week Monday. Question 1D, 2CEF, 3CEF, 4B, 5C, 7B. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 questions. Please show the work, write neatly, and then I'll grade them later. So, and also this is department suggestion. It says do all the questions from 1 to 8 and question number 15. We already did question number 15. It's about this thingy here. Matrix multiplication, why it's possible with the transpose. So you already did 15. And if you want to try, you can try 1 to 8, all of them, if you really want to try it. But if you don't want to try it, you definitely have to try these 9 questions. And guess what? The exam will be all from all the questions you're doing in the homework. Okay. And also I posted the review sheet. Did you notice that on Brightspace? I posted the review sheet. So exam will be from the review sheet, but the review sheet question are from the homework question. So do the review sheet very well.
When you say it's from the homework questions, is it from like the question issues? Oh, thank you.
So if you look at the review sheet, all the questions are from the homework. And the review sheet is based on the exam. So if you know your review sheet well, you know your exam well. You can do them well. Review sheet has more question, exam will have less question. But the same topic. Every topic you see, we'll see them in the exam. Now 1.4. So 1.4, the title is Matrix Algebra, same as our course name. Here we are going to learn what type of operation we do with matrices or how you do them. So first we start with some allowed operations with matrices. So when you add two matrices, this is same as you can change their position and add them. So A plus B is same as B plus A. If you add 3 matrices, you can add 2 matrices first and then the third matrix, or you can add the second 2 matrix first and then the first matrix, or you can add all the elements at the same time. When you multiply 3 matrices, you can multiply 2 matrices first and then multiply the third matrix with the product, or you can multiply the second 2 matrices first and then multiply the first matrix on the left. You cannot switch the position, but you can switch your order, in which order you are going to multiply your matrices. Order can be switchable, but the place of the matrices, it cannot switch them. And if you are adding 2 matrices and multiplying, this is same as you're distributing the 2 matrices, distributing the matrix into the sum. So you get AB plus AC. Or you can distribute your matrix from the right side. But if you do that, your right matrix has to be on the right side. So if you add A plus B and then multiply the result with C, you have to do AC. So you cannot do CA. It has to be A times C plus B times C. So from whichever position you're multiplying, you have to keep your matrix on that position. If you're multiplying from the left, then your left matrix should be the first one when you multiply. But if you're multiplying from the right, then the multiplication has to be on the right side when you multiply. If you're multiplying few constant first and then the matrix, you can multiply one of the matrix with the constant and then multiply another constant. So for multiplying constant, it doesn't matter the position. Same thing here. If you're multiplying two matrix and then multiplying a scalar, you can multiply the scalar with one of the matrix and then multiply the second matrix. Or you can multiply the scalar with the second matrix and then multiply the first matrix, but the position has to be on the left side. If you're adding to scalar and then multiplying with a matrix, you can distribute that. So you can multiply both scalar individually with the matrix, and then you can add the results. And lastly, what is missing? A is missing here. I'm missing an A here. So this is A times A plus B. You can distribute the scalar, and then you can add the two matrices. All of these are allowed operations. Now, like before, we know if you multiply A times B, it's definitely not same as B times A. So for example, here, our A is 1 by 2 and B is 2 by 1. So when you multiply AB, so for AB, what will be the dimension? Can you multiply AB? Yes, because we have the inner dimension same. So the result will be 1 by 1. And what type of matrix gets only 1 by 1? What's the name of that matrix? You will see. Let's multiply A times B. What do you get? 3 plus, so you multiply 3 and 1, and then you multiply 3 and 4, you get 8. And we have 3 plus 8, let me do it here. 3 plus 8, 11. So your matrix is only one element. That means it's just a scalar. So if you have a 1 by 1 matrix, it means just a number. It's not a matrix, just a number. Now let's switch the position, B by A. So what's the dimension for B? 2 by 1, and dimension for A? 1 by 2. So if you multiply, what will be the result? 2 by 2. So let's multiply. We have B, 3, 4, and you're multiplying 1, 2. It looks like 12. It's not 12, it's 1, 2. So let's do the math. 3 plus 1, no, 3 times 1. You go 1 row, 1 column. So this is your first row. This is your first column. Then you go the next column. Oops. So this is your 1 row and this is your second column. So it's 3 times 2 as a second column. 3 times 2. I mean, the second column. So the first column is only one element, 3 times 1. The second column is another element, 3 times 2. Then you move to your second row on the left. So you go 1 row, 1 column. So what do you have? 4 times 1. And lastly, we have 1 row, another column. 4 times 2. So row, column, it goes in the column position. Row, column, it goes in the second column. Then when you move to the next row, you have to change your row from the first row to the second row. The more you go row-wise in the first matrix, the more you go row-wise in your product matrix. So this is the first element in your left matrix. So this should be our first row in the product matrix. Then you do both column in the second matrix. They will be on the same row because we still are on the same first row in the left matrix. So left matrix will decide your rows for the product matrix. If you have multiple column in the second matrix, you are still going to be there. The result will still be on the first row in the product matrix because you're still on your you're still on your first row in the left matrix. So first row will decide your first row in your product matrix. The column you move, the more you move your second column, move your second matrix, the more column you're going to get in your result, in your product. But the row will be same. Then when you move to the second row, this will become the entire second row. The number of column, it depends on how many column you have in your right matrix. So the right matrix gives us number of column in the resulting matrix. The left matrix gives us number of rows in the product matrix. So we have 3, 4, 6, 8 as BA. Obviously, AB and BA, they are not same. They're completely different. AB is just a constant, but BA is a 4 by 4 real matrix. Okay, zero matrix. Zero matrix means all the elements in your matrix is 0. No other number, just a 0. So why do you care about 0? Well, sometimes we want to get result as zero matrix. Now the one interesting question. Find 2 by 2 non-zero matrices A and B. So they are non-zero means they have other numbers than 0 in them. But when you multiply, the result is 0. Can you think of 2 non-zero matrices? 2 by 2 for easy. 2 by 2 non-zero matrix. When you put them together, the result is a 0 matrix. So something, 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 something. When you multiply it, something, 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 the result will be 0, 0, 0, 0. So basically what I'm saying is, if you multiply this row with this column, the result will be 0. If you multiply this row with this column, the result will be 0. If you multiply this row with this column, the result will be 0. And if you multiply this row with the second column, the result is also 0. Can you find 8 numbers so that row and column multiplied gives us 0 result? Any idea? Let's start with something easy. Let's say I'm giving you 1, 1, 1, 1 matrix. Now figure out what should be the B matrix so that when you multiply row and column, they become 0. 1, 1, row wise or column wise? And then -1, -1. Okay, no problem, we can check. So 1 times 1 is 1, plus 1 minus -1 is -1, we get 0. Good. Then 1, 1 is positive, 1, -1 is negative, 0. 1, 1 is positive, 1, -1 is 0, negative, 0. 1, 1 is positive, 1, -1 is 0. Yeah, see? So you decide one of them, pick any number for one of them, and then based on that, pick the numbers for your B, so that the result becomes 0. It's a good observation, good choice. 1, 1, negative 1, negative 1. The surprising thing, the result doesn't have to be unique. You can pick any other another B matrix and you still get 0. Another good option is this one. We have 1, 1, 1, 1, and you can have negative 1, negative 1, 1, 1. This one also give you 0. Or you can do the other way around. 1, 1, 1, 1, and then 1, negative 1, negative 1, 1. This one also give you 0. So as long as you pick your first matrix, second matrix has so many choices. So all of these, the result is 0. Any question? Okay, let's see next one question. Can you find some non-zero matrices A and B, and then another matrix C, so that even though A and B, if you multiply A with C and B with C, they are equal. But if you cancel them, A is not equal B. So in reality, if you have AC equals BC, in normal algebra, we can divide both sides by C and we get A equals B, right? This is normal algebra, But we are in the matrix algebra, and we know division is not possible. So we want to see, even though the division is not possible, but what if somehow you get rid of the C matrix? For example, if you multiply, so we have, let me erase this. So we have AC equals BC. If you multiply on the right side, both sides by C inverse, they cancel out. And we're supposed to have A equals B, but we are not going to have A equals B. Can you figure out 3 matrices with this scenario? No one wants to use your brain? Okay, I have the answer here. A is 1, 0, 0, 1. B is 2, 0, 0, 2. And our C matrix is 1, 1, 1, 1. So if you multiply AC, so first row, first column, first row, second column, we get 1 plus 1. Sorry, 1 times 1 is 1, 0. So we have 1 here. Let me do the multiplication here. 1, 0, 0, 1 times 1, 1, 1, 1. So 1 times 1 is 1 plus 0 times 1 is 0. So first row, first column. Then first row, second column. 1 times 1 is 1 plus 1 times 0 is 0. Then we go to the second row. We have 0 times 1. So if you're confused about this, we have 0, 1, and 1, 1. So multiply 0 times 1 is 0, 1 times 1 is 1, so our result is 1. The next one is 0, 1, and 1, 1, same thing. So our answer is also 1. So you have 1, 1. So you have 1, 1, 1, 1. Our A and C is 1, 1, 1, 1. And if you observe A and B, definitely they are not same. So let's see what is B times C. BC. Or B, not BC, sorry. Yeah, BC. So this multiplication is wrong. It should be the other side. 1, 1, 1, 1. So if you do BC, we have 2, 0, 0, 2 and 1, 1, 1, 1. First row, first column. So we have 2, 0 and 1, 1. we have 2 plus 0, which is 2. First position. Wait, really? I did something wrong, right? It says AC equals BC. So AC 1001 and 1111. We get 1 times 1 is 1. 0 times 1 is 0. So 1 times 1 is 1, and 0 times 1 is 0. So 1, 1. And then 0 times 1 is AC equals BC. They don't match, right? Probably my ABC are wrong in the wrong order. 1, 1, 0. Yeah. Probably this is C and this is B. Who knows? But you get the idea, right? Let me erase all of this. So let me erase this side. Probably my ABC wrong. So probably A is 1001 and B is 1111 and C is 2002. Maybe, okay. These are from books, so you can check the solution at the end of the book. They have the solution. Any question? 2002. 2002. Yeah. Any question? Now something interesting. Power. When you apply power to a matrix, so normally if you have a number, let's say 2, and you apply the power 2, you do 2 times 2, you get 4. This is normal algebra, right? If you have, let's say 5, you apply the power 2, it becomes 5 times 5, so answer is 25. But now in matrix algebra, when you apply the power, it's the same concept. You're multiplying the same matrix power many times. So A square means A times A. A cube means A squared times A, or A times A times A. A to the n means you're multiplying A n many times. So you're multiplying the same matrix n many times. Now the question is, if I give you a matrix row-wise 3, 5, 2, 7, what would be the power of, what would be A squared for this matrix if we apply the power of 2? A squared means A times A, right? So we have 3, 5, 2, 7 times 3, 5, 2, 7. What's the result?
You want me to give you the whole?
You can give me the results. Row-wise or column-wise? 19, 15,
Oh, no, 19, 50.
or 50?
Oh, 20, 60.
20, 15, 59. Why I keep hearing 15? 59. Is she correct? You can verify her work. Who is lost in matrix multiplication? Anyone? Okay, so for you, I'll show you the multiplication. We have 3, 5, 2, 7 row-wise and 3, 5, 2, 7 row-wise. You take the first row and first column. You multiply them element-wise. So if you think writing this will be easier, you can write 3, 5 and 3, 2 column-wise so that you can see what you're multiplying. So we multiply 3, 3 and 5, 2. So we have 9 plus 10. The answer is 19. So this is first row, first column position. Then you go to the second column, but using the same row. So same row, but second column. So its position will be first row, second column here. And if you want, you can do the same thing. 3, 5, you can write column-wise. 5, 7, you can write column-wise. So you can see your work. You're multiplying 3, 5 and 5, 7. So 15 plus 35, answer is 50. Then once you're done with all the columns multiplying with the left row, you go to the next row. So this is our next row. You do the same math again. One row, one column. So we have 2, 7 and 3, 2. When you multiply, you get 6 plus 14. That gives us 20. So this is the position, second row, first column, because you use second row and first column. Then you do second row, second column. So this position, second row, second column. 2, 7 and 5, 7. You multiply this, you get 10 and 49. When you add, you get 59, which is here. So first row, first column gives us the result in the first row, first column. First row, second column gives us the result in the first row, second column. Once you're done with all the columns in your right matrix, then you go the second row in your left matrix. Then do the same thing. Second row, first column in the resulting matrix. Second row, second column in the resulting matrix. Second row, third column if you have more columns. And you keep going on column-wise and write the answer in row-wise. So you go column-wise, but write them in row-wise in the resulting matrix. Okay, so A square is 1950 row-wise, 2059 row-wise. But if you think A square means the element square, if you do element square, you get 3 square 9, 5 square 25, 2 square 4, 7 square 49. Are the same? You cannot apply your power in each element. In matrix multiplication, the power means multiplying the matrices, individual matrices, power many times. You cannot just put the power on the element. So power in the element is impossible. Okay. So in the exam, I'm going to ask this type of question as a short answer. This is A and this is A square. Is this correct or wrong? So I might give you this and say, is this correct? If A is this, is A square is this. So if you think, oh, the result has every element square, so probably this is correct, then you get 0. Okay. So these will be short answers like this thing. Now these are too hard, so not this. For example, here. Is AB equals BA? Is this true or false? AB equals BA or ABC equals BAC. Short answers like, okay. So like something that doesn't have big things, I'll give you short answers. For example, this one. Can you multiply A transpose A? Or can you multiply A transpose? So your exam will have few yes, no question, true, false question, fill in the blank question, few of them. And then the rest will be from the review sheet. So review sheet don't have these small things. But on the top, I said there will be some questions, small true, false question in the exam. So these are for those type of questions. So here it says, if A is this matrix and B is this matrix, find the operation A square minus B. So let's start with a square. 5, 3, negative 1, 2, column wise. We are multiplying the same thing, 5, 3, negative 1, 2, column wise. Let me write it smaller. 5, 3, negative 1, 2. Now volunteer for give me the steps or the answers. Would you like to try it now?
Yeah, sure. So we're doing, so it'll be, 5, 3, and then 5, negative 1.
No, you go one row, one column.
Yeah, okay, so 5, negative 1, in the first parenthesis, and then 5, 3 in the other one.
Mm-hmm.
And then you multiply 5 times 5 is 25, negative 1 times 3 is negative 3. Add them together, that's 26.
Mm-hmm.
And then for the next one, it would be 5, 5, negative 1. Well, with negative 1 and 2.
Mm-hmm.
That would be negative 5 and negative 2.
Mm-hmm.
And that's negative 7.
Mm-hmm.
Next one would be 3, 2 with 5, 3. And that would be 15 plus 6, which is 21.
Mm-hmm.
And then the last one would be again 3, 2. And now with negative 1, 2,
Mm-hmm.
which would then be negative 3 and 4. And that gave 1.
Good answer. Oops. Our answer here is 22, negative 7 row wise, 21, 1 row wise. Now this is take this a square and subtract your b matrix. So let's do it. Insert a square minus b. So we have 22, 21 column wise, negative 7, 1 column wise. And you're subtracting b matrix, which is 2, 2 column wise, 0, 1 column wise. Now this should be easy. Would like to try this one. Do you remember how they add or subtract matrices? Omar D, you look sleepy. Help me with this one, please. You're subtracting. (22 minus 2, which is 20. Negative 7 minus 0, which is negative 7. 21 minus 2, which is 19. 1 minus 1. There. Perfect. So this is your final answer. Any question? So in the exam, you'll have this type of question. Apply the power, add or subtract another matrix. Okay, now comes a new concept called identity matrix. Identity matrix are diagonal matrix. Means they have only their diagonal entries and everything else off diagonal are 0. So 2 by 2, and also one thing, identity matrix, they are only square matrix. Means they have 2 by 2, 3 by 3, 4 by 4, 5 by 5. So number of columns and number of rows are same. So identity matrix cannot have any uneven rows and column. They have to have same number of rows and column. Same number of rows and column, we call them square matrix. So every identity matrix is a square matrix, and they are also diagonal matrix. They're unit diagonal matrix. It means they have only ones on their diagonal. Everything else off diagonals are 0. So 2 by 2 has ones on 1, 1, 2, 2 position. Everything else is 0. For 3 by 3, you have 1, 1, 2, 2, 3, 3 positions. All 3 positions have 1, and everything else are 0. Identity matrix are only square matrix. And if you multiply a matrix by the identity matrix, whether on the left, on the right, it doesn't matter. The product is always the original matrix. So it's like 1. If you multiply anything by 1, for example, 2 by 1 gives you 2. Or 1 by 2 gives you 2. So it doesn't matter if you multiply 1 on the left side or 1 on the right side, you always get the same original number back. So same thing for matrix. If you multiply a matrix either on the left side or on the right side, it doesn't matter. The product is always A. So only for identity matrix, the position of the matrices doesn't matter. In reality, A times B is not B times A, but only for identity matrix, A times identity is identity times A. So identity is a very special matrix. This defies the other rule. It doesn't follow the other rule. And let's stop here. From in our next class, which is one sane person, we're going to work with identity more, inverse, symmetric, and then we're going to do some fun examples. And then you'll go to 1.5. So in our next class, I'm going to tell you our first exam date. So I'll decide when our first exam will be, and then you'll have another homework just for the exam.
So, for this one, I got 1 equals 3, which is consistent, but it's an infinite solution. Because there's more variables than the equation. And so to find the equation, I'm assuming I have to use the free variable. So
So
when
you
that,
have x1, x2, x3.
yes,
Your x3 is 3, and then your x1 is 2x2, and then minus 4x3, and then plus 1. So you know it's x3 is 3. So you're going to replace this here.
yeah, but for the x2, I just leave it as x2.
So this is not 1 equals 6, this is x3 equals 3.
No, I just meant like 1 equals 3 means it's like there's like an actual number. But yeah, I
Okay.
do know that. Unless you want me to label it as
You have
x.
to, you have to level. This is not 1, this is x3.
Okay, got it.
1 is the coefficient. So 1 x3 equals 3.
No, I know that, but I just wrote it. Like,
So when you write down the equation, you need all the formulas. What is x1? What is x2? What is x3?
oh, but you
So here your x3 is free variable and your x1 is not free.
the x2 isn't the
X2 is free because x2 is x2 itself.
Okay,
X1 depends on x2.
yeah,
And x3 has a unique
which
solution,
is 1.
which is
Or
3.
3, which is
So x3 has a unique number. X2 could be anything, and x1 depends on x2.
Hello, was that?
You came late, yeah. Remind me your name, please. Aaron. Okay, I told you many times. Here. Okay.
Thank you. With I, does it also count as like an increment too in matrix algebra?
Increment. I didn't think about that. Increment.
Since it's like kind of like a one.
I'll search about it. I have no idea.
Thank you.
So increment, you means like partitions, right?
Yeah, because I think like you can do minus I, like if you have A and you do A minus A times I, then that's kind of like
A minus A.
that's like I A times, like you're doing
If
like
you do A minus A times I is A itself.
yeah.
So A minus A gives you 0. So for subtraction or addition, it does.
So it is like an increment there
For addition and subtraction.
for addition and subtraction. Oh, but
For multiplication, you get the original thing back.
that's pretty cool. Yeah, like an increment.
Mhm.
Thank you.
Question, guys.
It's a pretty simple question, so.
No problem.
So